Okay, so we have a loop here that is 3.2 centimeters by 15 centimeters, and the center of the loop is located 5 centimeters away from this wire, right? Okay, so in our first example, or A of this problem, the current decreases from 14 amps to 6 amps in a time interval of 0.6 seconds. Alright, so our formula for the magnetic field of a loop is mu naught I, the magnetic field due to the wire, right? This is the magnetic field due to the wire inside the loop. It's mu naught I over 2 pi r. Okay, so that's that works out to be 56 microtesla when you plug in r is equal to 5 centimeters. Okay, now that's the initial, that's BI. The final would be mu naught times, it drops down to 6 amps, right? Over 2 pi r. And so that's only 24 microtesla, that's BF. Okay? And so delta phi B would be delta B A cosine theta, which in this case would be 3.2 times 10 to the minus 5, or 32 microtesla, times that area, which is 3.2 centimeters times 15 centimeters, and then the cosine theta term is just 1 because the magnetic field is perpendicular to the loop. So change in flux is 1.54 times 10 to the minus 7. The induced EMF, which is delta phi V over delta T, is 2.6 times 10 to the minus 7. And the induced current is just the induced EMF divided by the resistance, and that's 8.0 times 10 to the minus 7. Let me write that more clearly, 8.0. Alright, now to get the direction of it, well, our reasoning goes that delta phi B, now in this loop, the external field is going out of the page, but it's decreasing as the current in the wire decreases. Therefore, the induced EMF tries to replace those dots that are being lost. And if that's your induced EMF, if your induced EMF is out of the page like this, then that only happens if the current's going around like that in a counterclockwise direction. So the induced current is 8.0 times 10 to the minus 7 in a counterclockwise direction. Alright, now for part B, the loop actually moves closer to the wire. So again, here we are, and we've got our loop, but now the loop is moving closer to the wire. It moves 2 centimeters closer. So our initial magnetic field is 56 microtesla. Our final magnetic field is now, I guess it's mu naught times that same initial current, 14 amps, but now we're dividing by 2 pi times 3 centimeters, 0.03. And that's 93.3 microtesla. Okay? And so now delta phi B, like above, it's the same. It's the delta B, it's the magnetic field that's changing. The area of the loop is not changing, and the orientation of the loop is not changing. And delta B in this case is 37.3 microtesla, or 3.73 times 10 to the minus 5. And then we multiply by the area again, the area of the loop. And then again, the cosine theta term is 1, so that gives us 1.8 times 10 to the minus 7 volts. Sorry, that's Tesla. That's the change in flux, I guess, Tesla meter squared. And so the induced EMF is delta phi V over delta T. So I just divide by the time interval, and this took 0.45 seconds, so if I divide, that gives me 4.0 times 10 to the minus 7. And so the induced current is the induced EMF divided by the resistance, and we know that the resistance in the loop is 0.32 ohms, so that's 1.2 times 10 to the minus 6 amps. Now as far as the direction, well again we have that the flux delta phi b, the change in flux, well, it's initially out of the page, but in this case it's increasing as that loop gets closer. Therefore, the magnetic field of the loop is going to point into the page, okay, and so the current in the loop is going to be 1.2 times 10 to the minus 6, and then for an induced magnetic field that points like that, that means that the current has to flow clockwise. So there's our current for part B. Okay. Now for part C, we have the current. Let's see. So we have our long straight wire, and our current loop stays steady this time, but now it rotates along an axis, so it ends up being edge on to us. Right now the loop is face on, and it's going to end up being edge on. Okay, so the magnetic field in the loop is 5.6 times 10 to the minus 5 Tesla, or 56 microtesla still. That's the magnetic field in the vicinity of the center of the loop. This time, what's going to change the flux is going to be a change in that angle, a change in the orientation. And in this case, delta cosine theta initial is 1, and cosine of theta final is 0, right? When the loop is edge on, when we're looking down on it and it's edge on, that means that the magnetic field is parallel to the loop's plane. And so the theta term, the angle between the loop's normal and the magnetic field, is 0. So 5.6 times 10 to the minus 5, again multiplying by this area, 0.032 times 0.15, and delta cosine theta is just 1. So that's 2.7 times 10 to the minus 7, and that means that the induced EMF is, now this happens in what, 0.33 seconds, so if I take the 2.7 and divide by 0.33, I get 8.1 times 10 to the minus 7 volts. And so the induced current is the EMF divided by the resistance. The resistance is still 0.32. So I get 2.5 times 10 to the minus 6 amps. Now as far as the flux goes, again, the flux is out of the page initially. And in this case it's decreasing, right? It decreases down to 0. Right? Once the loop is edge on from our perspective, it's not pierced anymore by magnetic field lines. And so the flux drops from, I guess, 2.7 times 10 to the minus 7 Tesla meters squared down to 0. That means that the induced magnetic field of the loop is going to try to replace what's lost. Okay, and so if that is the induced magnetic field, that's generated by a counterclockwise current. So our current is CCW. So there's our final current of the 3.